In this video, we'll take a look at the temperature dependence of entropy of reaction. So the standard entropy of reaction is the change in entropy of a chemical reaction that occurs under standard conditions. IUPAC recommends using a standard pressure equal to 1 bar. Entropy of reaction can be calculated from the entropies of formation of the reactants and products. In terms of the symbol, we have delta S to represent entropy change, superscript circle to represent standard conditions, although sometimes a superscript plimsoll is used, subscript T for the temperature at which this reaction is occurring, and subscript R to denote that this is for a reaction. Okay, general form of a chemical reaction is shown here. We've got the reactants and the products. The stoichiometric coefficients for each component are given, as are the chemical formula for each component. So this is just a very general, generic form of chemical reaction. Also to note, stoichiometric coefficients for products are positive because they're being created through the reaction, and stoichiometric coefficients for reactants are negative because they're being consumed. So if we want to calculate entropy of reaction, we can use this mathematical formula here. Delta S of reaction equals the sum of the stoichiometric coefficient for each component multiplied by the entropy of formation for each component. So if we plug this in for the example given, we've got the stoichiometric coefficient for component 1 multiplied by the standard entropy of formation for that component, and we just keep adding those on for all of the different components present. Okay, so let's look at an example, remembering that stoichiometric coefficients for reactants are negative. We have the stoichiometric coefficient for methane equals -1 for this particular reaction that we're looking at. For water, it's -1. Also, remembering that stoichiometric coefficients for products are positive, we have +1 for carbon monoxide and +3 for hydrogen. We can look up values for the entropy change of formation for these different species, and then we can plug those numbers in to the equation. So for methane we have -1 multiplied by -80.70, and we can keep going through this, and we end up with an entropy of reaction at 298 equals 214.49 joules per mole per Kelvin. So we've been able to calculate this with these values that we can look up in tables. Okay, in terms of temperature dependence then, we can work out the entropy of reaction at a temperature that we're interested in, T2, based on knowing the entropy of reaction at a reference temperature T1, and also by knowing the change in heat capacity when the reaction takes place. So if we think about this reaction again and want to understand this change in heat capacity, we have delta Cp equals the sum of each individual stoichiometric coefficient multiplied by the Cp value for each component. Okay, we add those up and we can see an expanded form for this situation at the bottom of the screen. Okay, often we have the form Cp divided by R equals A plus Bt plus Ct squared plus D T to the -2. So on that basis, we can get a delta Cp divided by R by adding up each individual coefficient in that Cp equation multiplied by the stoichiometric coefficient. So for delta A, we need to sum up each individual stoichiometric coefficient multiplied by the A value for each component, and we can then work these values out. Okay, so in terms of going back to temperature change then, we've got an equation that we can use here. We've got the equation for the heat capacity, for the change in heat capacity. So if we just modify this slightly because we're dealing with change in heat capacity divided by R, we can actually change the temperature dependence equation for entropy of reaction and put in delta Cp over R within the integral, and then just put the value of R outside of that, so that if we wanted to, those R's would cancel and we could get back to the original equation. Now we're in a position to combine these two equations, and we've got a divide by t, so we can just tidy that up. We can now go ahead and do the integration, and finally we have an equation that gives us the temperature dependence for the entropy of reaction. So that's the overall equation that gives us the temperature dependence, remembering that we've got Cp in the form of Cp divided by R, with A plus Bt plus Ct squared plus dt to the minus 2, and that we work out those delta values by summing up the coefficients multiplied by stoichiometric values. Okay, so that's been a video about the temperature dependence of entropy of reaction. I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.